I will be talking about the design changes that I work on for Lab 3. The first design change was I decided to change the mode, or better yet, adding new modes. We decided adding two new modes, a relational mode and a reduction mode. So for the decoder, now we need a code that is 5 bits of input because we already used all the 4 bits inputs for previous modes. So we wanted to add, we have 10 new operations that can be performed. So we added another bit to account for these. So now in the decoder, all the input mode is going to be 5 bits. And here in the last part, we can see the new ones that we added. And so in the 3-bit LAU, we can see now that the mode in general, it's going to be 2 bits because now we need 4 different modes for our 4 different modes. So we have 0, 0, 0, 1, 1, 0, and 1, 1. And so we can see it here. We just added it on to our 3-bit LAU. So if we are guessing, if we want a mode 0, 1, that means it's our relational mode. And then we do operations with the numbers A and B that are being inputted. And we're going to be able to see that on the FPGA board. I will be showing some examples of how this works. The second design change that I want to talk about is a stopwatch that I decided to add into the decoder for our 7-segment display. And it has 4 modules in general, plus a top module. We have a clock generator module, which just creates the clock, and it basically makes it possible for the numbers to be displaying at so fast that we can see it all at once. Now, this clock that is being generated here is the input to our next module, which is the refresh clock, which basically tells the display in the FPGA board which digit to turn on. So we started with the rightmost digit, and we go on and turn on all the digits as the clock is being inputted here, as the clock changes. Our next module, which is the most important module, is basically where we have our counter logic and where we can see this clock taking shape. So we have 2 buttons, a start and stop button and a reset button. So we need to start its values of the buttons in order to not having to press it, keep it pressed for it to work. So we use a flip-flop for this action. And basically we have the 2 flip-flop registers and we have a signal register. What we want to do is if there is a difference between the value of the input button and its store value that we had previously on the register, then the signal is going to change and the clock is going to do what it needs to do. Here's where we assign all these values. If stuff happens, if the button and not the button and everything like that, we get assign the values to the signals, and the signals store these values. And so here we reach our counter logic where we have basically 3 scenarios. Scenario 1 is where we want to, if we're clicking the start stop button and the reset buttons, if the signals is 1, then basically you're resetting the clock. So you want all the digits on the display to be set to 0, and we do that here. And we're just standing at the 0 at this point. Scenario 2, we are running the clock and we stop the clock. So once we stop the clock, we want to save this value, because if we click the start button again by itself, then we want to keep going this clock from the same value. So this value must be stored somewhere. That's what we do in this case. It gets stored right here, and then we can keep going. If we press the start button again, it just keeps running from that number that is stored. And lastly, our third scenario we have is that we just want to start the clock, right? So we click the start button, which means that the numbers are going to start from 0 to 9. In the case that we're starting from the reset reset section. So starting from 0 to 9, from the rightmost digit to the leftmost digit. Once a number reaches 9, it resets back to 0 and it goes on to the next left digit. And so we use only 4 digits in our FPGA board that has 8. So our stopwatch goes up to 10 minutes, 9:59, if we want to be a little more exact. But this is kind of like the bigger part of our stopwatch. And after this, basically, we just have the 7-segment module with the case statements to turn on the required segments for each digit. And the top module, which just pieces everything together. And we can see the clock, and I'm going to show you how it works with the FPGA board. Here's our stopwatch in action. This button will start the count. It just keeps incrementing. Once it reaches 9 in a digit, it will go back to 0 and go on to the next digit. If we want to stop it, we use the same button to stop it. It's safe to count, and it continues on from the same count. And in order to reset it, we must stop it and hit the reset button, and it goes back to 0. Lastly, we're going to do a reduction NOR, again on the number A, which is F in this case. And if we do reduction NOR on the number 1111, we should get a 0. And there is our answer, and we see that it works. Now I want to talk really briefly of the main difficulties of this section of the lab. I was hoping to get the stopwatch to be incorporated into our decoder, which is the one that runs the 7-segment display. For this, I was going to have an input, let's say it could be a switch, a button, anything really that could be set to 0 or 1. And I wanted to have a decision that if this thing was set to high, then maybe I could run the stopwatch module instead of running everything else that would show the instructions in hex and so on. But after some research, this is really not a programming language like C++ or another object-oriented programming language, Python, whatever it is. So we're coding this hardware, and we can't just call something on a condition just like that. I did a lot of research on this. I couldn't find a way to do it. I think the way was to do it inside the 7-segment display, inside, I guess, this module that we have for displaying the results of the LAU, for displaying the instructions. I thought we could do it in here, given a certain condition, if I was to incorporate all the modules for the stopwatch here somehow. But I couldn't, after several tries, I couldn't get that to work very well, so I decided to leave it separately. And I guess that would be my next challenge for the next lab, where we'll still be working on a clock.
Okay, so this is our FPGA board. This is the code for the lab. As you can see, the name of the module is called system, and its function, it was to combine our ALU, our decoder, and our 7-segment display, which is this. And for this lab, what I did was I wanted to implement not only the switches as inputs, but also the push buttons over here. So to do that, in our code, I rather replaced one of the inputs as a button, which is the bits from these push buttons here. So that'll be 4 bits, and that was going to be the very last digit of the display. So we're going to demonstrate it right now. So originally we had 4 bits, and 4 bits to complete our 12-bit instruction input. So for the first number on this end would be here. So we can have 1, 2, 3, 7, 8, F all the way. And for the next digit, we have the remaining 4 switches. Here, 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 here. Those have F there. Because it's from binary to hex conversion, which is what our code does. And originally we'll have the remaining digit come from these switches, but I changed them to these buttons. So as you can see, we can have the first bit, second bit, third bit, and 4th bit. And another thing that happens, which is cool, is that if you hold 2 numbers, it then combines the 2 inputs into 1. And yeah, It also goes all the way to F as well if you hold all 4 buttons. Yeah, so it works. So as you can see, a difficulty that we have is getting it to remain or stay as the display. You have to hold it down, which is kind of yeah, so you have to hold it down. But that was a difficulty that I had. I couldn't figure out how to do that and implement that in the code. So, but it still works, and yeah, that's what we have for our lab.